Alright, we have made it to the last lecture for test 3, and this one is a little lengthy, but we're going to be covering pretty much the same stuff, so it's not a lot of different things, just showing the different forms that the graphs can come in. So we're going to look at graphing square root and cube root functions, and then we're going to look at graphing circles. Alright, so first, when we're graphing square root functions, the parent function of the square root looks like f of x equals square root of x. And you know we've learned for function notation, f of x is equal to y. So this is really the same thing as y equals square root of x. It's just given in function notation. With the square root function, there is a definite endpoint. So in order to graph it, we need to determine the endpoint, and the easiest way to do that is to find the domain. So remember, the domain is the set of all x values that we can plug in to this function square root of x and get out a valid answer. So we can take the square root of 0, we can take the square root of 1, we can take the square root of 10. 10 is not a perfect square, but it still has a square root. So basically anything 0 or bigger. The only thing we can't take the square root of is something that's negative, okay? So to find the domain, which will help us find the endpoint, we're going to take the expression that is under the square root, which in this case is just x, and we're going to say it has to be bigger than or equal to 0. So all that's saying is what we just said, that I can take the square root of 0 and I can take the square root of any number that's bigger than 0, which would be a positive number. So this number right here is the x where my endpoint is going to occur. So that's the first number I'm going to put into my table. Now, if you will, on your notes, I prefer that these charts look like this. In the first column, we're going to choose x values. In the middle, we're going to figure out what its corresponding y will be. So y equals whatever the function you were given is. And then in this last column, we're going to write the ordered pair, okay? So I'm going to plug in 0 for x, and that tells me that y is equal to 0. So for my ordered pair, when x is 0, y is also 0, okay? Now 1 point isn't enough to make the graph, we need some more points. So by the domain, we can choose anything, any x, that is bigger than 0. So we could choose 0.25 here if we want to. We could choose 700 if we want to. But of course, we're going to try to keep our numbers contained to this 10 by 10 graph that we have. And we're also going to try to make the math easy on ourselves. If we are taking the square root, then choosing perfect squares will make things simpler, because let's pick 1 here for instance. That one is the next one up from 0, and it's also a perfect square. So if I plug in 1, then I get 1, 1. But what if I just kept counting and I chose 2? So if I did that, that one's not a perfect square. So I'd pick up my calculator, put in square root of 2, and it tells me that that is approximately 1.41. So there is nothing mathematically incorrect about that ordered pair, but it's not an exact point, so it's going to be difficult to graph. So normally, if we're dealing with square roots, we want to try and get something underneath the radical that is a perfect square for that reason, because we don't want something that's hard to graph. So the next perfect square from 1 would be 4. So let's plug in 4. And I get if x is 4, y is the square root of that, which is 2. And then the next perfect square is 9. So if I plug in 9, the square root of 9 is 3, and we get the point 93. Alright, so I'm going to graph this one, this one, this one, and this one. I showed you this one as an illustration of why we really don't want to choose numbers that aren't perfect squares. So we have 0, 0, 1, 1, 4, 2, and 9, 3. So remember, this first point is an end point, which means there won't be an arrow there. It's just going to be the dot. But the domain is everything bigger than or equal to that 0, so it means it goes on forever. So we're going to connect the dots and use an arrow on the end. Alright, so that is what the parent function of the square root looks like, and by parent it means there's no shift involved. Alright, so the next thing, once we know what the general square root looks like, then we start to look at shifts. Oh, some reason this stuff didn't print to the screen here. Hopefully it is on your papers. It printed on mine. This is supposed to be f of x equals the square root of x minus h right here. So the first type of shift that we're going to look at, a left or right shift of the graph, occurs if the change takes place under the radical. So you see this time I don't just have x underneath the radical. We have this h, which is just going to be some number. When that happens, when the change is under the radical with the x, it's going to be a left or right shift. Okay, so let's look at what we would do. Oh, this one is supposed to be f of x equals x minus 2. Okay, so just like the first one, I need to determine the endpoint, and we can do that most easily first by determining the domain. So remember, we take the expression that's under the root, this time it's x minus 2, and we say bigger than or equal to 0. That part never changes. If I solve this for x, I would add 2 to both sides, and we get x bigger than or equal to 2. So this is going to be my endpoint, and that is the first value for x that I'm going to use. So just choosing perfect squares this time is not going to work, because you notice my endpoint 2 is not a perfect square. What's happening is because there is a shift, now we're going to need to shift the x's that we choose to get perfect squares. So my first set of perfect squares is 0, 1, 4, and 9. So if you notice from the parent graph, my first x was 0, and this time it is a 2. So to get from that 0 to the 2, we added 2, right? So that's what we're going to do to get our other x's. We're going to add 2 to each one of them. So 1 plus 2 is 3, 4 plus 2 is 6, and 9 plus 2 is 11. Alright, so let's plug those in. I'm going to put y equals square root of x minus 2, and then my ordered pair. So let's plug these in. If I replace x with 2, we get square root of 0, which is 0. So this first ordered pair, if x is 2, y is 0. If I plug in 3 for the x, we get square root of 1, which is 1. So you see so far, it's working out. I'm ending up with perfect squares under my root. And that's what we wanted. If I plug in 6 for x, we get the square root of 4, which is 2. And finally, if I plug in 11, we get square root of 9, which is 3. So by shifting all of my perfect square x values by adding 2, I ended up with perfect squares under the root, and it gave me my nice numbers I wanted again. So we have 2, 0, 3, 1, 6, 2, and 11, 3. So we're going to have to kind of guess at 11 a little bit and put it here. And remember that first number is my end point, and we're just going to connect them and continue with an arrow. So you notice when I have x and it is minus a number and it's all up under the root, we got a right shift. So basically it took that parent graph, picked it up and shifted it to the right. Alright? So the next one is f of x equals square root of x plus 2. And we're going to use the same tactic. First I'm going to find the domain. So I'm going to say x plus 2 bigger than or equal to 0. If I subtract the 2 to solve for x, I get x bigger than or equal to negative 2. So I know negative 2 is going to be my endpoint. So this time, if I look at my original set of perfect squares, the first one was 0, and now it's negative 2. So this time we didn't add 2, we subtracted 2. So I'm going to subtract 2 from each of those perfect squares to get my x values. So 1 minus 2 is negative 1. 4 minus 2 is 2. And 9 minus 2 is 7. Alright, then we're just going to plug them in. So if I replace x with -2, I get square root of 0, which is 0. If I replace x with -1, I get square root of 1, which is 1. If I replace x with 2, we get square root of 4, which is 2. And lastly, if I replace x with 7, we get square root of 9, which is 3. Alright, so these are my points. We have -2, 0, -1, 1, 2, 2, 7, 3. Again, that first point is my end point. We're going to connect them and continue off forever. Alright. So you notice for this one, if I have underneath the radical plus a number, this one gave me a left shift. Alright. For the next one, this one is supposed to say f of x equals square root of x plus k. And this one, you notice the k, which is just going to be some number, it is outside of the radical. When the change is outside of the radical, the shift is going to be up or down. So for the first one, f of x equals square root of x plus 3. This one is a little simpler. The up and down shifts are generally easier to choose the x values than the left and right shifts, because now the only thing that's under the radical again is just the x. So that means we can just use the ones that we know are perfect squares. The domain, of course, if you take what's underneath and set it bigger than or equal to 0, that tells me to start with 0 again. So the biggest thing is just be careful about whether everything is under that radical or not. For this, we're just taking the square root of 0, which is 0, and then adding 3. So this ordered pair is 0, 3. If I put in 1, we get 1 plus 3 is 4. If I put in 4, we get 2 plus 3 is 5. And lastly, we get 3 plus 3, so we get the 0.96. Alright, so if we graph those, we have 0, 3, 1, 4, 4, 5, 9, 6. So we still have that first point as an end point, and then we connect them going off forever. So you see this one, if the change is outside the radical and it's plus, then it is shifting up. So I bet you can probably guess that for this one, it is outside of the square root, and it is a minus, so you can probably suspect that this one is going to shift down. It's like the one above. For the domain, the only thing under the radical is x again, so we get to just choose our perfect square values. And then if we plug them in, the first one gives me 0 minus 3. So we get 0, negative 3. If we plug in 1, we get 1 minus 3 is negative 2. So we get 1, negative 2. If we plug in 4, we get 2 minus 3 is negative 1. And last, if we plug in 9, we get 3 minus 3 is 0. So we get 9, 0. So this one, we got 0, negative 3 for the endpoint, 1, negative 2, 4, negative 1, 9, 0. And we just connect them and continue forever.